Guys, so today we are gonna do not a very popular reaction but a very useful one, which is known as Barton decarboxylation, and it is named after a British scientist called Sir Derek Barton, who was awarded the Nobel Prize in 1913. Now in this reaction there are many decarboxylation reactions, but this one is quite useful because there are no side products obtained in this reaction, and the mechanism of this reaction is that it proceeds via a free radical mechanism. So we'll look into it. For those who are just looking for a brief overview, I would like to just tell you that there's this carboxylic acid, then we add this group. This group is known as a thiohydroformate group, and in presence of DCC DMAP, I'll be talking about these two, what these two things do in detail after when I am talking about the mechanism. Then we get this ester, and then we add a radical initiator in the form of AIBN. It could be any radical initiator, like benzoyl peroxide is also a radical initiator. And then we add tributyl tin hydride, which is basically donates its H radical, and then we get the alkane with one carbon less. So let's just look into the mechanism of this reaction. Now DMAP is nothing but it's 4-aminopyridine, and you can draw a pyridine basically, right? And then these are two methyl groups attached to this. Now this is a very good base. It's actually a better base than pyridine as well, because of the resonance stabilization in case of this DMAP. So this is known as basically DMAP, and it is particularly useful for activating. It's basically a nucleophilic. It acts as a nucleophilic catalyst, and DCC is nothing but this kind of group, and then we have cyclohexane attached. This is DCC. It does nothing but it activates the carboxylic acid. It activates the carboxylic acid. How it does that is when when O minus is formed, this O minus then attacks this particular carbon over here, and we get a electrophilic group which can be easily removed. Okay, so now let's look into the mechanism. So firstly we get this is the ester. Let's draw the ester first, right? This is the ester, and this is attached to the O, like that, C double bond O R, right? So this is the group that we got. This is the ester. Now what happens over here is, this is very important. So AIBN is basically a free radical initiator, so it generates a radical. So let's say it generates a radical called I, and when this radical reacts with Bu3SNH, this reaction we get IH plus Bu3SN radical. So we get this radical, okay, Bu3SN radical. Now this radical, what it does is, I'll just write it down over here. It goes and reacts to this sulfur, okay, and because of this, what happens is this there is this bond, a nitrogen and carbon bond over here. So what it does is that this comes like this, and one of the radical goes like this. So I think it's not clear. I'll just I'll draw it over here. What we are going to get is basically nothing but this group, and to one of this we have SN Bu3. So this we get, and meanwhile we also get this, basically gets into this, plus we get one more group which is R C double bond O, and this is radical over here. Now what happens is, since CO2 is very stable, it would like to get removed as CO2. So what happens further is that, so we get this goes over here and this goes over here. So we get CO2 plus R radical. Now we have Bu3SNH, as I told you, like we have more of Bu3SNH. Now this R radical that is generated, it reacts with this tributyl tin hydride. We get RH plus again the radical. So this is the chain propagating step. So this is how the reaction further continues, and we get no side products for this reaction.